The last topic we're going to look at is equilibria involving solutions. So things dissolved usually in water, but not necessarily only in water. Now, the nice thing for solutions is, again, what's going to matter is the activity. That's what's going to show up in our equilibrium expressions, as we talked about in the last video. And in this case, the activities values for solutions are not equal to 1. We can't just ignore them. Instead, at low concentrations, we can make an approximation that the activity of component J is about equal to the concentration of that component. And so that's what you learn to do in general chemistry, and what we often do in chemistry for solving equilibria involving solutions is that we say, oh, the activity and the concentration are about the same. Let's just plug in the concentration for the activity, and it shows up in the equilibrium expression, right? So you would have your K value would have the concentration of, a component Z raised to the new Z, right? Say that was one of your products, and one of your reactants, A, was also present as a dissolved species in solution. You just use the molarity, and your standard state, your A naught, is equal to a 1 mole per liter solution. So all of your concentrations need to be in molarity, and that's often what's considered the standard state. And so we can simply use, and you've done this in other classes, we won't go through this in a lot of detail in this class. You use these along with partial pressures in bar, and solids and liquids don't show up, and you can do everything and calculate equilibria just like you would for the gas phase species we were looking at. Now, sometimes activity coefficients are necessary, though. So just like we talked about with the fugacities, sometimes you need to use activity instead of concentration. Instead of this approximation, maybe it breaks down. In particular, when you get to higher concentrations or high ionic strength solutions, where the activity and the concentration diverge pretty significantly. And there's an example from your textbook that we'll work through here to show how you might think about this. So say we have barium fluoride solid in water, and we're looking at its solubility. Now KSP, which is the solubility product, as a reminder, that is for this reaction, barium fluoride solid in equilibrium with its aqueous ions. Okay, KSP for barium fluoride is very small. It's 1.7 times 10 to the minus 6, which means mostly this is an insoluble compound, and very little of it dissolves into barium and fluoride if you put some of the solid into water. Now, if we want to write this out accurately, KSP is equal to the activity of barium 2 plus times the activity of fluoride squared divided by the activity of barium fluoride. Now, the nice thing is that this on the bottom is equal to 1. So we can say we have the activity of barium and the activity of fluoride squared. That is our that's our equilibrium constant. Okay, so if we want to write out the write this out using activities instead of concentrations, we have to use the activity coefficient. So we'll end up with gamma plus minus cubed, because we have 3 activities there. We have activity of barium and activity of fluoride squared. So gamma plus minus cubed will be times the concentration of barium times the concentration of fluoride squared. Okay. So then we can rewrite this expression in terms of concentrations instead of activities. Right, so take the concentration terms, that'll be equal to KSP divided by gamma plus minus cubed. Okay, so what we can do to actually solve this is, what's going to happen is, depending on the amount of ions that dissolve, the ionic strength changes, which changes the activity. So we sort of have a circular thing going on here, and we'll solve this by iteration. So we'll start with gamma plus minus equal 1. This would be ignoring activities, right? If we have the activity coefficient is equal to 1, we're just treating this as a concentration question. And we know that the concentration of barium, if we call that S, the concentration of fluoride is equal to 2S, right? We get twice the number of ions. So we can then use this to solve our equilibrium. So we'll get S times 2S squared is equal to KSP, which is 1.7 times 10 to the minus 6. And we get S is equal to 7.52 times 10 to the minus 3. And since all of this was in molarity, we get moles per liter for this. All right, so that tells us that our concentration of barium in the solution would be 7.5 times 10 to the minus 3, and our concentration of fluoride would be twice that. It would be 1.5 times 10 to the minus 2. Now, what we can do is then, now we know our concentrations, we can use that. We can use S in the Debye-Huckel formula to calculate the ionic strength and calculate what log of gamma plus minus is. And then we can plug that back into our equilibrium. Now, what I'm going to show here is not using the extended Debye-Huckel theory, just regular Debye-Huckel. And I'm going to skip some steps here. They're outlined in the notes, and I'd like you to, you can make sure that I'm doing this correctly. But basically, we're going to say, okay, log gamma plus minus is equal to negative 1.173. Absolute value is Z plus, Z minus, times IC to the 1/2, right? This is the Debye-Huckel formula we can use. So we need to calculate IC based on the concentrations of barium and fluoride. If we do that, we get 1/2 times plus 2 squared times 7.52 times 10 to the minus 3. That was the concentration we just found. And then we'll have our fluoride, which is minus 1 squared and twice that, right? So 2 times 7.52 times 10 to the minus 3 molar. And if we do that, we get an IC value of 0.0226 moles per liter. And then we can plug that into the Debye-Huckel formula. If we do that, we get that log of gamma plus minus is equal to negative 0.353, or that the activity coefficient, the mean activity coefficient, is 0.703. And now we iterate. Now we take that value and plug it into our equation up here, all the way back here. The activity coefficient shows up down here. So we plug in, we know KSP, we know gamma plus minus cubed, and that will give us a value that we can then solve for the concentration of barium, concentration of fluoride. So when we do that, our next step on the iteration is using that activity coefficient, we can find a new value of the concentration and the new ionic strength, and then repeat this process. The final, using the not extended, just the regular Huckel equation, is that gamma plus minus is equal to 0.645, S is equal to 0.012 molar. I'm skipping a bunch of steps here just to, this video is already getting long enough, I don't want to go into too much more detail here. But the key point here is that the ideal situation where we ignore activities, we got a concentration for barium of 7.53 times 10 to the minus 3 molar, 7.52. And whereas if we use activities and activity coefficients and remember that the ionic strength matters, we get a concentration of 0.012 molar. We can see that's a pretty significant difference. It's not quite double, but almost double the concentration that we would predict based on using activity coefficients and taking that into account. So this is an example of why we care about activities and activity coefficients, why you've learned about it, is that it does make a difference in equilibrium calculations, particularly in things involving ions or things at high concentrations. And that is the end of chapter 26.